All right. This day, honestly, it took me a little bit to kind of realize how I wanted to approach this. It might have been because I'm rusty, but I think overall I wrote a solution that I'm pretty happy with, so that's what I'm going to go over. So if you look at the question for day 3, you basically get this kind of grid, and what they want you to do is look at each of these little symbols, something that's not a period and not a number, and then find all the numbers that are adjacent in one of the 8 directions, so any of these, and find all of the numbers like that, and then sum them up for part 1. So first things first, a way of parsing this information. I'm a big fan of using dictionaries in Python, and also a really nice trick that I've learned from Advent of Code is using complex numbers. So all you need to know from a complex number is you basically have a real part and an imaginary part. And you basically end up getting like a 2D point, but it's just built into math and it has some nice little properties that we're not using at this point, but it also does have some nice coding properties, which you'll kind of see in a little bit. So right off the bat, I'm just going to go ahead and do this. So complex is how I create a complex number. And this basically just takes in 2 arguments. I'm just calling it P so it looks like a point. And hopefully this makes the code a little bit more readable. So now let's go ahead and create a grid. So a grid is going to be a dictionary. And we're going to populate this by iterating over this 2D array that we get of characters. So the way that I'm going to do this is I'm going to do for y and line in enumerate input.split lines. And then if I just go ahead and sanity check this, if I print this out, you can see let me do this in just a test case. Here, you'll be able to see that we're getting each line as a little y value here, and then we're getting the line itself. And then now we'll go ahead and do this also for here. Here for x and whatever the value is in enumerate line. So by following this pattern, if I do x, y, and v, I'm basically getting each of the x and y values along with the actual character itself. And so like, for example, if we see 9, 9 here, this corresponds to this square. And then if I look at 7, 9, we're getting this 8 here. So now I'm just going to save all of these to this grid. And then I can do something like this. So I'm going to use our little complex class. So we get a little point is equal to v. And we'll see, this will make a little bit more sense why I'm using complex numbers in a bit, so just bear with me. And so right now, if I just do this, my grid is going to be kind of huge. Oh. There, sorry. But here, grid's going to be kind of big because it carries all of these extra periods, and most likely all of these are going to be garbage. We're not going to need it. So let's go ahead and not actually include those. So if v is not equal to a period, then we will go ahead and save this into our grid. Why does it keep doing that? Oh, sorry. I know why. It's because I'm doing a keybind to change between these 2 windows like this. And apparently it's getting rid of the argument. My bad. But so here, now you can see we've cleaned this up and we're going from all this extra garbage to just the data that we need. So now the second question that we have to kind of address is how are we actually going to first like get these adjacent squares? So for example, and even before we do that, let's probably save the symbols themselves because we can iterate over these at some point. So I'm going to create might as well just, here, symbols, and we'll just make a list. Why not? We'll do if v is numeric, like we did on, I think, day 1. And if it's not numeric and it's not a period, we know it's a symbol. Then we'll do symbols dot append, and then, our point, because we want to actually use these coordinates later. So now we have 2 little variables here. So if I look at my symbols and my grid, we end up with, here's your little list. And we can see 3 plus 1j. J is basically how Python says complex, like I you'd see in math. But now we have basically 3x and 1y. If I look here, 0, 1, 2, 3, and then 0, 1. At 3, 1, we end up getting our kind of symbol. So that's good. That's what we want. And then now let's figure out a way of getting all of the adjacent squares. So the nice little thing about complex numbers is if I treated this like a tuple, like if I just did something like this, my code would look more or less fine. And it would be maybe a little bit more readable. But the problem here is now, if I want to find, like, for example, 1 space to the right, I can't just go ahead and do something like 4, 3, plus 1, 0. If I try this, Python is going to do something weird and actually it's going to, let me count this out, it'll basically just concatenate these together. And that's not what we want. And it doesn't make sense if I'm doing something like minus 1, 0. It's going to freak out. But if I go ahead and make these complex numbers like this, now it's just regular math, and these are defined. And so we end up with 4, 3 minus 1, 0 gets 3, 3. And so we can do math with all this stuff, and it ends up making your code a lot cleaner if you're willing to kind of handle this. If not, you're still fine. It's just a little bit uglier code. So now, if we want to get all the adjacent squares, what I can do is if I have like some point and it'll be like p and it's equal to 0, 0, I could add basically -1, -1 would give me like a top left. Like 0, 1 would give me top middle. And then 1, or sorry, this would give me top middle. And then 1, -1 would give me the top right, and so forth. And so if I go ahead and define all of these, all right, so I went ahead and copied this over. And so what we have here is we have our little grid with all of the extra coordinates that would give us different directions. So here, top left, all the way down to bottom right, not including this middle one, because we don't really care about that for adjacent. So since we're going to use this in a couple different places, I'm going to go ahead and also define this up here. So now, and just to make sure we're not getting any weird syntax errors, if I run my code, everything's fine. Cool. All right. So now that we have this, let's see how we can get our actually adjacent squares. So if I go ahead and let's start kind of cranking out question 1. Let's create a function to get adjacent parts. So we'll call it def get adjacent parts. It'll take in our grid and it'll take in some position. And so what this should do is, for example, if I'm here and I give it this, it should go look at all of these adjacent parts and find me the actual number itself and return those. So from this, if I look here, this adjacent parts should give me, first of all, it should take the position and it should iterate over all of these different directions. So we'll do for direction in adjacent. If I do print pause plus d, and we'll just go ahead and call this right now. So we'll do get adjacent parts, and I'll call this on, I'll give me its grid just because we need it for now. If I call it on 0, 0, cool, another thing about complex numbers, we can see it basically gives us all of these. And if I give something like 1, 0, so x is 1, y is 0, it still works. So this is all nice and dandy. So now for each of these points, we're going to want to actually see if it's a number. And second of all, we want to make sure we're not counting the same number twice. So the way that we're going to do this is we're going to create a function here. And we're going to call this get num. And it's going to take in a grid and a position. And what this function should do is I should be able to drop it in, for example, oh shit. All right. I hope the scene was right, but here we're going to create this get num function. And what it should do is if I give it, for example, this point here, it should go and find me this 35 without duplicating this over. And so it should also, the reason I'm saying not duplicate is if I give it this 3 here, I want it to still read this 35, but it should give me some way of distinguishing to make sure these are the same number. Just on the off chance, if I have something like 633 here and a different 633 right under it, I want to read those as different numbers. So in this get num, what I'm going to do is, first of all, I'll check if pause in grid, or if pause is not in grid, pause for position. So if this position is not in the grid, that means it's either off the boundaries or it's one of the periods that we didn't save. Or if grid at pause is numeric, and we want to see if it's not this. So here, this code will only run if we are either at a period, out of bounds, or it's another symbol or something that's not a number. And so if it's any of these things, let's go ahead and just return none. And so otherwise, by here, we can assume that pause is in grid and is a digit. All right, I'll just leave it like that. So now the problem is if I get, for example, I'm here and I'm checking this top right corner. I'm getting this 3 here, but I want to read this entire number. So how can I do that? So the way I'm going to do that is I'm going to start off and I want to move wherever this position is, I want to move a little variable back until we get to the start of the number. So I'll do this. While pause -1, so the coordinate like 1 to the left of it is in the grid, and it is also a digit, then I want to actually move position back by 1. So what I'm doing here is if I'm at this location or this location, then we check here, position -1, make sure that it's something in our grid, and then also make sure that it's a number. If that's the case, then we change pause to whatever that variable is by subtracting 1 from it. And then we keep doing this. And then eventually, once we get to here, pause -1, this square will not be in the grid. So the loop stops. So now position is going to be the leftmost point. We're going to save this to some variable, start, and I'll explain why we have this in a second. And then now we actually need to read what the number is. So we're going to do something like num is equal to an empty string, because these are all strings so far. And we'll do while pause in grid, and grid pause is numeric. Then we want to go ahead and we should append whatever the digit is. So we'll do num plus equals grid at pause. And then we'll also go ahead and move position 1 to the right. And then now, finally, we can return our start position, and we want to turn our num into an integer. So let me go ahead and kind of recap what this function is doing. When we start off, this get number, we want to be able to give it some coordinate, and then if it's a number, it should give us the entire number and some unique way of telling us what the number, like which number it is. And so the way we're doing that is, first of all, returning none if it's not a valid thing. Second of all, we move whatever variable we got all the way to the left of the number by continually moving back until we run out of digits. That's here. And then we record that position, and this is our unique identifier. So for example, if this right here was a 633 also, they would be different, and we could tell that because this start coordinate would be different. So we return that, and then we build up the string by basically looping through and then adding that to a string and finally turning it back into an integer. So now that's our get number function. If in our get adjacent parts, we'll go ahead and create a set. And the reason we're using a set is so it automatically gets rid of duplicates for us. So we'll do parts is equal to a set. And then for each different direction in adjacent parts, or from each different direction from our position, we're going to go ahead and do parts. And we want to basically increment, or we want to union this with, wait, let me make sure I'm not stupid. All right, sorry, we're doing add because we're just adding one element, and we'll do get num grid at whatever our position is plus our direction. So let me explain what this line is doing here. First of all, so a nice thing about Python set is it's kind of like a math set where it doesn't allow for duplicates. And so when we have our parts.get add num, all this, we're basically taking our position, adding whatever direction is, and then calling our get num, and finally adding that into our set. And so for a little example, if I'm at this star here, we're going to go through all of these different directions in our adjacent function. And so we'll go up here first. We'll call get num on this square. Get num will go ahead and grab us this entire number, and then it'll return it, and we add this to our set. Then we try here, and then get num will return us none because of this, and we'll add it to our set. And then we'll do this here also, and we get another none. But since it's none, it's not going to add it to the set again because the set does not have duplicates. So that's going to happen here and here also because those are both none. And then when we get to here, it's going to read this whole number, save it to the set. When we get to here, the little cool part happens. It's also not going to add it because we already have a 35, which starts here. And so if I go ahead and I'll actually just return parts, And just as a little quality of life, I'm going to get rid of the none element if it exists by using a set difference here. So if I now go ahead and I call get adjacent parts, and I call this on the star here, which is going to be at x 0, 1, 2, 3. So we'll call this on parts 3, and then it's at y value 1. Let's see what we get. Oh, I didn't print it. My bad. And I also have to pass in grid. Oops, here. So now, that's not ideal. Let's see what's going on. So when I pass in 3, 1, and let's make sure that this is in symbols, so let me just print out symbols. Yep, it's in... Oh, I never changed this back. That's my bad. So now that these are all points in our grid, we can see this outputs two things here. We output at 0, 0, 467 right here, and we also output at 2, 2, a 35. Perfect. And just to kind of prove that I'm not insane, if I go ahead and I modify this test, so I'll have a, we'll make this 467 also. And notice how we're getting two different numbers because we're adding that start value. So that's just a little edge case that we count for. Maybe we don't need it, but it's good to have it. All right, so now what we can do is we can go ahead and call this on every single symbol here. So if I go through this get adjacent parts, I'll just call this on every symbol. So if they're def part 1, we'll take in a grid and a list of our symbols, and we'll create an answer variable for 0. Oh, sorry. Here, we're going to go ahead and create a list of our parts. And now for S in symbols, and we're going to union whatever we get from our get adjacent parts called on our grid at position whatever the symbol is. And then finally, we'll just do part 1 is equal to 0 for P in parts. Part 1 plus equals P at 1, return P1. So what we're doing here is we iterate over all of our unique parts that are adjacent by 1 square. Then we go ahead and sum up all of the actual values itself. Because remember, we're returning a tuple where the first one is the start position and the second is the number itself. So now if I go ahead and I make this part 1 grid, or the symbols, let's see what we get. All right, we get 4,361. If I look at add a bit of code, that's what we're getting for the test case also. And if I go ahead and run this on my actual input, I get 540131, and that's also my answer. So that's good. All right, for part 2, what they want us to do here is they want us to only find the gears, which a gear is defined as like some symbol with a star, only if it's touching exactly 2 numbers. And then finally, we want to add up the gear ratios, which is multiplying those 2 numbers together. So in this instance, we would basically get this star would be a gear, and we have 35 and a 467. We'd multiply those together, add that to our total. This is not a gear because it only has 1 number touching it. This one is a gear because it has 2 numbers touching it. And we do that pretty much. So the nice thing is now we can just go ahead and in our code, we'll do def part 2, grid symbols, and hopefully kind of the design choices I made earlier make a little bit sense now. Remember, I'm recording this after I've already solved all of it. So we're going to go ahead, and since we want to be summing up all of our things, we're going to have an answer variable and eventually return that. And let's just go ahead and get this out of our way now. Return part 2, grid symbols. So now, for S and symbols, we want to only look at the asterisks. So if if grid in S, to get the actual character, is not equal to a star, then we'll continue, which is basically just skip to the next loop, or like skip to the next iteration of the loop. And then, so by now we know that S is a star. We'll do parts is equal to get adjacent parts at grid and our symbol. And then if the length of parts is exactly equal to 2, then we know we have a gear. And then we want to just find a way to basically multiply the two values of our set together. And so we could do something ugly like this, where we have parts. The problem is we can't really get parts 0. Like if I just go ahead and run this, it's going to complain because a set is not subscriptable. What that means is I can't just index into a set because they're not really ordered. That's how they kind of do all their magic of making sure they have no duplicates, all that. But a list is, it's indexable. So we'll just do this. And if I go ahead and show this, it works, but we're just adding something weird now. So what I can do is I can do parts at 0. And this will give me the first part, and then we have to get the actual value. So we'll do this times parts at 1 and the actual value itself. And if I run this on the test case, I get 467,835. 467,835. If I go ahead and run this on my input, I get this huge number, and that's what we get for the answer. So hopefully this makes sense. And also, regarding the comments, a couple of people asked about this whole test suite. I'm going to try to record a different video right after this, and I'll upload it in the same playlist. And so, yeah, I'll try to keep these videos updated before the next day comes out. Good luck. Have fun.